Hi there and welcome. This is section 9.4 of our applied calculus class. We're doing approximation of definite integrals. So in this, we won't really do any calculus. We'll be doing algebra and computation. We're going to say that the integral from a to b of f of x dx using the midpoint rule is going to be about equal to, you take the f of x at that point x1. Notice I've broken it up into sections here. So you'll find at that x1 and then times whatever size this width is. So it's the width times the height there, or width times length, width times length. So that's what we're doing, is we're breaking up any curve f of x, and we're just making these rectangles at various points along f of x, and we're just going to say, hey, the area under there could be about equal to, just add up those different areas of the rectangles. So let's do this. We're going to approximate the following integral by the midpoint rule. And n equals 3 means we're going to break it up into 3 rectangles. So we've got the integral from 1 to 4 of 2x minus 3 quantity cubed dx, and we're going to break this up into 3 rectangles. So we need to know, if we're going to break it up into even rectangles, how wide are they going to be? So in order to figure out what that's going to be, I'll just say b minus a, so that's our 4 minus 1, divided by 3. So it's going to be 3 minus 3. So they're just going to be 1 apart. So from 1 to 2, 2 to 3, 3 to 4. That's 3 sections. The endpoints of the 4 subintervals begin at a equal 1 and are spaced 1 unit apart. The first midpoint is in between 1 and 2, so that would be 1.5. The midpoints are also spaced 1 unit apart. According to the midpoint rule, the integral is approximately equal to, just substituting this into our midpoint rule by plugging in that value of 1.5. So this is 2 times x minus 3. Our first x is 1.5, our second x is 2.5, and our third x is 3.5. Adding all of that together, I'll get 72. Now, there's another rule. That was the midpoint rule. Another rule that we can do no calculus and just estimate by using trapezoids. It might get us a little bit closer. So the integral from a to b f of x dx using the trapezoidal rule is, you'll just take the function at this first point a naught plus 2 times the function at a1 plus 2 times a function at a2 plus 2 times a function at a3, blah, 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 all the way till you'll get to the end. Now notice that beginning point and the end point are not multiplied by 2. All right, and then we will multiply that by the delta x over 2. So, and that's just following a trapezoidal area calculation. So let's approximate the following integral by using the trapezoidal rule. I've got the integral from 1 to 4 of 2x minus 3 quantity cubed dx. We're going to break it into 3 trapezoids. Just like last time, we saw that they are 1 unit apart. So the endpoints of the subintervals are a naught is 1, a1 is 2, a2 is 3, and a3 is 4. I usually draw these out for myself whenever I am solving them by hand. So here we go, just plugging it into the trapezoidal rule. We get this area is 90. There's another rule that you can do, and it's called Simpson's rule. So Simpson's rule says that what I'm going to do to calculate the integral is find f at a naught 4 times f at x1 plus 2 times f at a1 plus 4 times f of x2, blah, 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 all the way till you get to the end. Notice the beginning points and the end points don't have multipliers. And this is all times delta x over 3. So of course we need to do one using the Simpson's rule. Let's do the same thing again. So we're going to do the exact same integral we've been doing, that integral from 1 to 4 of 2x minus 3 cubed dx, where n is 3. Once again, as in the last example, delta x is 1. This gives our endpoints of A0 is 1, A1 is 2, A2 is 3, and A3 is 4. Plugging those into Simpson's rule, I get that this area is 78. Now, although this happens to be the exact answer, remember that Simpson's rule is just an approximation and therefore generally yields only an estimate of the exact answer, not the exact answer itself. It's just Simpson's rule is better. You know, we do each of these different rules, the midpoint rule, and then the trapezoidal rule is usually a little better, and then the Simpson's rule is a little more complicated, but it's a little better. So the Simpson's rule does tend to get a little closer on. Now, in order to figure out how much error there is, what we are going to need to do for error analysis is just a simple measure of the error of an approximation to a definite integral is the quantity approximate value minus actual value, and give me a positive answer. That's what the absolute value symbols are for. Okay, that's pretty easy, just subtract. And that's the error. Yeah, of course. So the error of the approximation theorem, let n be the number of subintervals used in an approximation of the definite integral. Number 1, the error for the midpoint rule is at most a, which is the number such that the absolute value of f double prime of x is less than a for all x satisfying x in that interval to a to b, times b minus a cubed all over 24n squared. The error of the trapezoidal rule is at most a, which is the number such that the absolute value of the double second derivative of f of x is less than a, where we took the absolute value of that for all x satisfying in that interval where x is in between a and b. That's going to be a times b minus a, quantity cubed over 12n squared. Likewise, Simpson's rule is basically the same thing for that. Notice that a times b minus a to the fifth over 2,880 n to the fourth. So let's play. Let's obtain a bound on the error of using the midpoint rule where n is 3 to approximate our same integral that we've been working with. Now here, a is 1, b is 4, and f of x is 2x minus 3. So let's differentiate this twice so that we can get that f double prime of x is 48x minus 72. And let's figure out what our error is going to be. So how large could f double prime of x be if x satisfies anywhere in between 1 to 4? So since the function 48x minus 72 is clearly increasing on the interval from 1 to 4. In fact, it's increasing everywhere. Its greatest value occurs at x equals 4. Therefore, its greatest value is, plugging in that 4 to 48 times 4 minus 72 is 120. So we may take a equal 120 in the preceding theorem. The error of the approximation using the midpoint rule is at most, plugging all of that in, 15. Now, we have determined that the exact value of this integral is 78 and that the midpoint approximation is 72. Therefore, this approximation was in error of 6. Our result in this exercise says that our midpoint approximation error should be no greater than 15. Since 6 is no greater than 15, this result suggests that our midpoint approximation was done correctly. All right, if you need any help with this, be sure and email me, rweaver10@alaska.edu. Have a fantastic day.